Welcome to another lecture on molecules in motion, and we will continue on the explanations of whatever we had in the Debye-Huckel theorem, and we are trying to explain the Kohlrausch's law, where you have the molar conductivity dependence on the concentration in terms of under root of concentration is what we are trying to explain. And what we have done in the last class, I am going to summarize, because we are going to do a extension of the Debye-Huckel law. So, what we have in the summary, Debye-Huckel theorem was when we Debye-Huckel law, what we had done in the last class was we were looking into the mean ionic coefficient of the electrolytes being proportional or being having a dependence of under root of the ionic strength, and that was the basis of what we had in Debye-Huckel law was based on the having a ionic atmosphere around the central ion. So, we are going to be looking into the summary of what we had talked about in the last class. So, the Debye-Huckel theorem dealt with the distribution of ions around a central ion, and based on that a equation was derived on the qualitative treatment of interionic interactions between the neighboring ions and the central ion. What we had visualized, we had put in the concept, we had discussed the concept of ionic atmosphere, which can be visualized as a spherical haze of opposite charge around a central ion. Each ion in solution is on average surrounded by ions of opposite charge, and a slight imbalance of the charge arises from the competition between two effects. The two effects are, one of them is the motion, thermal motion of the ions. What does the thermal motion do? If you have a central ion, it is surrounded by a haze of oppositely charged ion, and this haze which you have where along the central ion, the number of the counter ions will be always outnumbering the central ion. However, the total charge, we have a total charge neutrality, that means the charge of the central ion should be balanced by the haze of oppositely charged ion, despite the fact that the haze of oppositely charged ions will be having a higher number of charge associated with themselves. So, if we have each ion on average surrounded by ions of opposite charge, then what causes imbalance? There is two competitive forces which is acting. One is the thermal motion of the ions, and the other is the Coulombic interaction between the ions. What does the thermal motion do? Because thermal motion or thermal energy, we say it is kT, the Boltzmann constant into the temperature in Kelvin. So, kT is the thermal energy. So, thermal energy is always there associated with any temperature of the system. So, whenever you have the ions in solution, the thermal motion, what does it do? The thermal motion tries to distribute the ions uniformly throughout the solution. But there is another sort of force which is acting in an electrolyte solution. It is the Coulombic interaction between the ions. Coulombic interaction means if you have oppositely charged ions, then you will have experience attraction. If you have oppositely same charges, then you similar kind of charges, then you have a repulsion. So, if you have a ionic atmosphere, if you have a central haze, spherical haze around a central ion, then what can cause this disturbance of the spherical haze around the central ion? One is if there is a if imbalance between the two, the thermal motion and the Coulombic interaction between the ions. So, if either of them is if the Coulombic interaction is more effective, then it takes over the thermal motions which is trying to distribute the ions uniformly. So, the Coulombic interaction becomes a major player in the field. So, what we have? We have the theory which was going to be modified by Onsager in 1926, and that was the basis of the modern theory of strong electrolyte, and the theory is known as Debye-Huckel-Onsager theory. And the equation which was derived, see, all of these are experimental observations based on which we try to model and formulate equation which will regenerate or reciprocate, or we can get back the observed values using this formulated equation. So, these are model equations which is trying to explain something which is experimentally existing. Okay. So, the Debye-Huckel-Onsager theory for a strong electrolyte is the basis of what modern theory of strong electrolytes is known to us. So, Debye-Huckel-Onsager theory for a strong electrolyte shows for a strong electrolyte the value of molar conductivity at infinite dilution is much less than unity. And the fundamental idea under this work is based on the electrostatic attraction or electrical attraction among the oppositely charged ions, and this affect the speed of the ions when placed under an electric field, and this is known as the interionic effects. So, what we are talking about? We are talking about that if we have a strong electrolyte, what the observation is that you have the molar conductivity depending on under square root of the concentration of the electrolyte, and at infinite dilution it is less than unity. And the fundamental idea lying behind this is the electrical or electrostatic attraction among the oppositely charged ions, which affects the speed of the ions when they are placed in an electric field. So far we are talking about only the electrolytes in solution which were dissociated. Each ion was surrounded by a haze of spherical charge, and we had not talked about them being affected under any electric field. So, if we have an electric field associated with a charge, central charge surrounded by a ionic atmosphere, a spherical haze of oppositely charged ion, then what happens? The speed of the ions with which the ions are going to move gets affected because of the interionic effects. And what are the two major interionic effects associated with the electrolyte system? One is called as the relaxation effect or asymmetric effect, and the other one is the electrophoretic effect. Let us see what each of them means. So, what we are trying to explain? We are trying to explain the square root of molar concentration of a strong electrolyte's dependence on the molar conductivity, and the two effects which is associated with the ionic atmosphere, which tends to reduce the mobilities of the ion, and hence the conductivities are the ion-ion interaction, reduction of ionic mobility due to retardation of ionic in the presence of the ionic atmosphere, and because of the enhanced viscous drag due to ionic atmosphere moving in the opposite direction. So, these are the two effects which play when we have an ion in a electric field. So, what we have, if you look at this picture here, you have a central ion surrounded by oppositely charged ion, that is, here we have taken positive charge as the central ion, and it is surrounded by negative ions. Okay. So, this is a symmetric haze which we see. It is a spherical symmetric haze around the positive central ion. You can have a similar one with the negative ion being the central ion. That is not the issue. Issue is when you have these ions which is not under any electric field, you have a symmetric haze around the central ion. And we see that we have the molar conductivity is at infinite dilution is less than 1. That means, when you have the molar conductivity dependence not on C, but under root of C, is what we are trying to understand. And why is that we are trying to interpret the lower value of molar conductivity in terms of the retarded value of the ionic movement in the solution. And the retarding values, retarding motion of the ions in under existence of an electric field can be explained on the basis of the ion-ion interaction. One is the reduction of the speed of the ion due to relaxation effect, and another is the reduction in the mobility or the speed of the ions because of the electrophoretic effect. So, let us see what we have. This is the symmetric charge, which is still. Now, suppose we have a ion in the placed under an electric field. Suppose you have a negative electrode here, then the positive charge will go towards the cation will move towards the cathode. So, the cathode suppose is here, it is moving towards the cathode. Then what you see, then the charge atmosphere which was surrounding them gets distorted. When it is moving forward, the charge atmosphere, ionic atmosphere, it is not completely formed, while the one which is behind is not completely disappeared. Let us look at this. So, in absence of an electric field, what we have, the ionic atmosphere is spherical and symmetric around the central ion. That is what we have seen. But in presence of an electric field, cations move towards the cathode, anions move towards the anode. We are focusing only on the positive charge. Obviously, you will have a negative charge very close by, but we are focusing on one particular central ion to have a simplistic picture. Okay. So, in presence of an electric field, the cations move towards the cathode, the anions move towards the anode. This leaves a large number of oppositely charged ion behind than in front. So, in the front, the ionic atmosphere is not formed, while this has moved. What is having what we have a large number of oppositely charged ion which was part of the ionic atmosphere being left behind. So, what happens? The center here you see the center of the central ion and the center of the spherical sphere coincide, but here the center of the charge and the center of the sphere which we have ionic sphere do not coincide. This symmetrical spherical symmetric ionic atmosphere is distorted. The centers of the positive and the negative charges no longer coincide. Okay. So, you have generated some sort of a asymmetry in the charge and the surrounding atmosphere. So, this is what we have. The overall effect is the excess opposite charge which is left behind, some of them are left behind, tries to drag the moving ion from moving forward, and in the process slows down the forward displacement of the central ion. Okay. The center of the charge of the displacement of the center of charge of the atmosphere is a shorter distance behind the moving ion. The attraction between the opposite charges, the retards the motion of the central ion. What is happening is essentially the rate of formation of the new ionic atmosphere of the central ion, which we can visualize this. This is the central ion which we have, it is moving forward. So, as they move forward, they will have a ionic atmosphere generated, but what happens? The ionic when the ions are moving, they are moving pretty fast, and the amount of the ionic atmosphere which should be generated does not have the time to be formed. While what you have is the ions which were forming these negative charges, which is now the center of the negative ions is some sort of distorted than that of the central ion corresponding to the central ion like this. So, this is no longer symmetric. Here you have the center of all the negative charges coinciding with the center of the positive charge. Here we do not have all the negative charges, the center of all the negative charges do not coincide with the center of the positive charge. Positive charges moved forward, but what is happening? The charged the ionic atmosphere for the forward moved ion has yet to be formed, but what happens? The formation, the dispersed ion atmosphere which is having is not completely disappeared. What is the effect of it? Effect of it is this is going to this positive charge is going to have experience a attractive force from behind because of the undispersed ionic negative counter ion atmospheres. Ionic atmosphere because of the counter ion. Like if you have a positive, it is going to be the negative ions which is going to be pulling it back. If it is a negative ion which is moving forward, then it will be the counter ions of the positive ion charges will be trying to hold it back. So, the rate of formation of the new ionic atmosphere is not the same at which the previous ionic atmosphere disappears. Suppose you have in the same time the ion is moving, immediately the charge is forming an atmosphere and this charge has disappeared, then you will not see a effect. But what you have, then the ions will move under the electric field as it is. But what happens when you have the ion moving forward, but the ionic atmosphere is not yet formed, but the one which was there around the central charge, which is now moved forward, is going to pull it back because of the electrostatic force of attraction, because they are counter ions. And what will happen? This will tend to retard the motion of the central ion. So, the rate of formation of the ions is not the same, rate of formation of the ionic atmosphere is not the same for the ion which is moving forward. The previous one is not completely disappeared and the new one is not completely formed. So, there is a relaxation period, and that is why this we call this as a relaxation effect. So, there is a relaxation time involved. In case of the moving ions, there will be always an excess of ions of opposite charge. The ions will always be dragged back. This affects the mobility of the ions and hence the conductivity. If mobility is increased, conductivity increases. If mobility decreases, conductivity decreases. So, the whole effect which we see because of the asymmetry of the ionic atmosphere or because of the different relaxation time, the relaxation time of the ionic atmosphere which is formed and which is getting dispersed, which is formed and which is left behind, the formation of the new atmosphere, ionic atmosphere, and the disappearance of the previous ionic atmosphere do not match. They have a time lapse, or we can say there is a relaxation in time. So, this effect which is going to eventually have effect on retarding the motion of the central ion by pulling it back when again subjected against a electric field is known as the relaxation effect or the asymmetry effect. Asymmetry effect comes from the concept that the ionic atmosphere around the central ion is not going to be symmetric anymore, because the ion is moving under experience of the electric field is moving faster, and the opposite counter ions is still to be dispersed and they tend to have an attractive force on the central ion and try to pull it back. So, this is the relaxation effect which is associated with the reduction in the mobility or speed of the molecules when subjected against in a electric field. There is another effect which we have talked about, which is another ionic interaction, is the electrophoretic effect. You just see what we have, you can see the picture here. You have a central ion, you have suppose this side is the cathode, positive charge is there, the positive charge is going to move towards the cation is moving towards the cathode, that means the negative electrode. So, what happens when the ions are moving under the electric field? If you remember, when we were talking about we were deriving the drift speed, we had seen that whenever an ion is moving under an electric field, it experiences a viscous drag. Now, if there is an ionic atmosphere present, this drag is going to be enhanced, because of the ionic atmosphere moves in the opposite direction to that of the central ion. So, let us see what is there in this diagram. What you have an electric field applied this side. So, the ions are going to be moving this side, right. So, we have a frictional force which is going to be existing, which is going to draw the ions backward, and the frictional force and the electrophoretic retarding force will try to pull it back. So, what is this electrophoretic retarding force? What you have when you are moving the charge under the electric field, we have said that the ionic atmosphere around the charged ion is not going to be formed, the one which is previously there and the ion is moving forward, this is not going to be distorted, so which is not going to be dispersed so easily. So, what happens, some portion of some amount of the oppositely charged ion will be always there. So, these you see when we are having an ion moving this side, the forward ionic atmosphere of the charge is not yet formed, but the one which was there around this central ion is not completely dispersed, it is still existing. So, these ions are still existing, which is trying to pull it back. This is associated with the ionic atmosphere. Now, see what happens. You have the frictional force coming from the medium itself, because the solvent is going to be now attached to the ionic atmosphere. So, these are the solvent molecules which we are looking into. When we are talking about an ion moving towards this side, then another application of electric field, what you have, this force, this is the electrostatic force which is going to be generated for the new ionic atmosphere, which is going to be yet to be generated completely, but you have some amount of ionic atmosphere which is distorted and yet not disappeared. This solvent molecules will get attached to it, and then you have the frictional force as well as the electrophoretic force. This enhancement in the viscous drag is what is known as the electrophoretic effect. Okay. So, the concept wise, both electrophoretic and asymmetric effect will reduce the movement of the ions or reduce the mobility of the ions, because both of them, in both the cases, the ion is trying to move forwards towards the direction of the cathode for a positive ion, but it is dragged behind. For first one, for asymmetric one, it is dragged behind by the not completely dispersed ionic atmosphere. And when you have an electrophoretic effect, this not dispersed ionic atmosphere will get associated with some solvent molecules, and this solvent molecules which is attached to the ionic atmosphere will move in the opposite direction, and hence will try to retard the motion in the direction of the applied field. So, what we have? We have produced a friction due to which the mobility of the central ion is retarded. So, what we have here? We have the two effects, which is the asymmetry effect and the electrophoretic effect, which is interplaying playing together. We do not know to what extent the electrophoretic effect is relevant and to what extent the asymmetry effect is effective, but both of them play together for the ions to be retarded in motion. So, whenever the ions are retarded, so if the ions are retarded in motion, that means their mobility is reduced. Both the effects, electrophoretic and the relaxation effect gives rise to a loss in mobility. They retard the ion from moving forward, and this is hence going to reduce the mobility of each of the ions and hence the conductivity. Okay. So, if a solution is very dilute, we can apply the solutions which we have looked into, but if the solution is not very dilute, what happens? The motion of the ions are retarded because the electrical attraction between the opposite ions, between the ions of opposite sign, opposite charge, and also because the positive and negative charges are moving in the opposite direction and carry the solvent molecules. Both of these intensify as the concentration of the electrolyte increases. So, whenever we are talking, so far we had talked about a very dilute solution. What we are now putting it, if the dilution is not sufficient, is not equal to 0, then what is effectively going to be concerned is if the concentration is increased, both of these effects, the relaxation effect and the electrophoretic effect, is intensified as the concentration of the electrolyte increases. So, what happens when you increase the concentration, the retarding forces are more effective, and so this mobility of the ions are going to be reduced, and so will be the conductivity. Okay. So, we will take into account what are the factors which are going to affect the electrophoretic effect for a particular system, and what are the effect which is going to be important when we talk about the relaxation effect. These two factors and how the new equation of the Debye-Huckel-Onsager theory is developed, and what is the close monitoring of what based on the formulation which we have, we do the experiment and see the experiment, how the experiment result or how far the experiment result is close to whatever we have formulated in the Debye-Huckel-Onsager theory. Thank you so much.